model that not only produces single value predictions, but also a quantification of uncertainty, quantifying how confident we are in these predictions. And we'll see how this works during this talk. But before that, a little bit on who I am. My name is Quan. I'm a PhD student at Washington University in St. Louis, and my research revolves around Bayesian machine learning and decision-making under uncertainty. And in my research, I use a lot of Gaussian processes, or GPs, so it's a topic near and dear to my heart. So I'm pretty excited to be talking about this with you all today. You can find me on these social media links, especially my GitHub repo, where you can find the slides that we'll be looking at today as well. Okay, so with that out of the way, I'd like to start with this simple motivating learning example. So let's imagine that we are trying to fit a simple one-dimensional regression model on this data set of 3 training data points, visualized as these black axes here. So these data points, right, they're observations from some unknown target function that we're trying to learn. The blue solid line that I'm showing is the predictions made by this kernel-rich regression model. We don't have to know what that model is, but it's just a common ML model that people usually use in the real world. So I said that the predictions generated by this model is single value because at each test point that we're interested in, we only have one single number to represent our prediction. So for example, at x equals -1 here, our prediction is around -0.25. Around x equals 3, our prediction is around 0.25 or 0.5. And this is not just a particular characteristic of kernel-rich regression, right? It's most typical ML models work this way, where it just produces single value numbers as predictions. And that's something that I particularly don't like about these models, and I'm hoping in this talk I'll convince you of the same thing. Specifically, there's this drawback that there's no error bars, no quantification of how confident or how uncertain we are about the predictions we are generating. And if you are building a model in a setting where you want to use these predictions to inform your decisions that you may make in the real world that might have serious implications, then this lack of uncertainty quantification can lead to a lot of serious problems, specifically lack of trust from the user. So, and I like to say again, right? This is not a problem with just kernel-rich regression, but other models like a decision tree or a neural net also has this problem. And I'd like to kind of talk a little bit about this lack of uncertainty quantification a little bit more. So while we are making predictions with a machine learning model, right, there's this regime where we call interpolation, where we're trying to interpolate between 2 training data points that are close by, for example, this region. We are saying that we're interpolating because we're just imagining how the unknown target function that we're trying to learn from behaves between 2 training data points. But we also have extrapolation, right, where we are trying to make predictions about the target function when we're further away from the training data, where we don't have a lot of information. And in terms of uncertainty, or in terms of confidence, uncertainty should behave differently when we are interpolating versus when we are extrapolating, right? When we are interpolating, we are close to our training data. So for example, this point and this point, then our uncertainty when we are making these predictions should be low. But when we're extrapolating, when we are farther away from the training data, then our uncertainty should be high. Again, with this kernel-rich regression model, we don't have this kind of distinction of uncertainty when we are extrapolating versus interpolating. And this is where the Gaussian process or the GP comes in, right? It works, and we'll see why this is later in the talk. It works by accounting for how similar each test point that we want to predict on is to the training data points that we have access to. So the predictions generated by a GP has 2 components. The first is this solid blue line again, which just shows mean prediction. That is the most likely values that the labels that we're trying to predict take. But we also have this shaded region that shows 95% confidence intervals or error bars, which quantify uncertainty about a prediction. And these error bars achieve exactly what we wanted, right? Where if we are interpolating over here, we have pretty high confidence or low uncertainty, right? Quantified by a very narrow error bar. But when we further away from our training data, we are extrapolating, then this error bar increases gradually to quantify our increasing uncertainty. So that's very nice to have. And this principal quantification of uncertainty leads to increasing use of the GP in recent years, especially in decision-making under uncertainty applications, like we said, where we have to carefully reason about what our models know and don't know. So in this talk, I'm hoping to talk about the underlying mathematical intuition behind the GP, and we'll see how this principal quantification of uncertainty is realized with the GP. And the punchline, and this is, I guess, spoilers, but the punchline is basically that a GP is just a generalization of a multivariate Gaussian distribution to very high dimensions. And by using a multivariate Gaussian distribution to model correlations between different random variables, we achieve this quantification of uncertainty that we really like in a GP. So in this talk, we'll see how this is actually achieved. And I've had a chance to talk about GPs with a couple of different types of audience. And it seems to me that to talk about the GP is the easiest with this particular example that we'll look at on this slide. So let's imagine a toy scenario, right, where you've been living in St. Louis, Missouri, which is where I go to school. But you just got a new job and you're looking to move away to a new city. So you want to sell the house that you're currently living in. But a problem that you're facing right now is that you're not actually experienced with the housing market. So you don't actually know how much you should set the price of your house at. So imagine that you're talking to your friend, right? And you said, oh, I don't have a pretty good guess. So anything between 100K and 300K is probably okay. But I would like to narrow down this range because it's very big, so it's not very informative. And what you'd like to have is a reference point, a price of someone else's house that they recently sold. So your friend comes along, right, and they said, oh, this person that you know, Alex, sold her house for $250K. You actually misheard your friend, though. You thought that your friend meant Alex, who's living in California. So a completely different person living in California. So you said that, oh, that's a pretty low price for a house in California, but that doesn't really help you narrow down the original price range, which is between 100 and 300 again. This is natural, right? Because knowing the price of a house in California doesn't really help you with selling a house that you have in St. Louis, Missouri. But your friend actually corrects you, saying that, oh, it's actually Alex, your neighbor, instead. And upon realizing this mistake, you said, oh, that's really helpful information because not only the two houses are close by, but they are also very similar. So that helps you a lot in narrowing down an appropriate price for your house, which is now just between 190 and 270. So what exactly happened in this conversation, right? And what does it actually have anything to do with GPs and uncertainty quantification? We could realize the connection by kind of framing this conversation using the language of machine learning. So in the beginning, right, what we have is an inference task where we want to predict the price of our house, which is so predicting the label of the test point, the price of our house. Now, your friend comes along and to offer a potential training data point, which we interpreted as just the price of a house in San Francisco. And we said that this is not pretty helpful because this training data point is pretty far away from the test point. It's very different. It comes from a completely different distribution. So that's not going to be very helpful in predicting the predicting the label of the test point that we're interested in. But upon realizing our mistake, right, we see that, oh, this training data point is actually the price of a neighbor's house, which is a very similar data point to the test point that we're interested in. So that would be very helpful indeed in helping us with the inference task, with predicting the price of our own house. And as we'll see in this talk, even though the GP works in a more slightly complicated way, the basis of the GP base comes down to this procedure of comparing whether a test point is similar to some training data point or not. And by using that measure of similarity, we can generate these predictions that come with uncertainty quantification or error bars that we're really interested in. And we do that, again, by using multivariate Gaussian distributions. And some of you might be familiar with the base case for the multivariate Gaussian distribution, which is just a univariate Gaussian distribution or a one-dimensional normal distribution. The probability density function, or the PDF of this distribution, you might be very familiar with it. It's just the regular bell curve that we are showing on the right. And each distribution, right, is parameterized by two numbers. The first is the mean, which is just at the center of the bell curve, and then the variance, sigma square, which defines the spread of the bell curve. So if we have a random variable x that follows this normal distribution, then mu, the mean value, would be the value that x most likely takes, and sigma will quantify our uncertainty about whether x will actually take on some value that's close to mu or not. This uncertainty is also quantified by this object, which is called the confidence interval. A 95% confidence interval is exactly equal to mu plus and minus 1.96 sigma, which is this region that I'm showing on the right here. We're calling it a 95% confidence interval because this range consists of 95% of the probability mass of this distribution, or 95% of the area under the curve. And sometimes we also use this notation, which is this bold arrow bar here, to indicate this confidence interval. Okay, so this is the base case, right? The univariate Gaussian distribution case. But we can also generalize this distribution to higher dimensions by accounting for multiple variables at the same time. And that's what we get when we use a multivariate Gaussian distribution. Using a multivariate Gaussian distribution, we model not only the distributions of individual random variables, but also the correlations between those variables. And we still have two mathematical objects to describe the mean and the covariance of this multivariate Gaussian distribution. Here, because we're working with multiple random variables, we have a mean vector mu and a covariance matrix sigma. The mean vector here is, again, describes it basically concatenates the different values that the different random variables most likely take. And most of the time, we just normalize this mean vector to the zero vector without having to worry about it. But the covariance matrix is actually more interesting. It, again, quantifies the spread of the individual different random variables, but also the correlations between them. And more specifically, right, the diagonal entries of this covariance matrix describe the variance of the variables. So, for example, sigma 1,1 will be the variance of x1, sigma 2,2 will be the variance of x2, and so on. The off-diagonal entries describe the covariance of the corresponding pair of random variables. And we'll see an example of this right now. So let's imagine, right, that we're working in a 2D case where we have two random variables. So what we have is a bivariate Gaussian distribution. And what we can do is we can plot out the probability density function, or the PDF again, now as a heat map in 2D. So the darker colors here are showing higher probability density values, right? Higher probabilities. So looking at this, right, we first noticed that the spread of x1 horizontally is smaller than the spread of x2 vertically. And this makes sense, right? Because the variance of x1, which is 1, is smaller than the variance of x2, which is 3. But more interestingly, we see that this heat map is slanted to the right, which shows that there's a positive correlation between x1 and x2. So if x1 takes on some high value, then x2 is also likely to take on some high value. And this is explained by this covariance between x1 and x2, which is 0.9, which is quite big. But if we don't have a positive correlation between the two variables, right? If the covariance is exactly at 0, then what we have is this symmetric PDF where regardless of which value x1 takes, the distribution of x2 doesn't really change because, again, there's no correlation between x1 and x2. I really like this heat map PDF visualization because it not only tells us, right, the distributions of the individual variables, but also the correlations between them. But when we move to higher dimensions, when we have more than 2 random variables, then we cannot really easily plot out the PDF anymore. It's not really easy to plot a function in 3D or in higher dimensions. So what we can do instead is to use this alternative visualization, which people usually call the parallel coordinates plot. And what we do is we plot out the 95% confidence intervals of individual random variables in parallel. So here we have x1, here we have x2, and here we have x3. Note, though, that we are not really visualizing the correlations between the different random variables, but that's the best that we can do with this kind of plot. Okay, so this slide, right, has been about using multivariate Gaussian distributions to model individual random variables and the correlations between them. But that's only one half of the story, actually. Another part of the story that we're interested in is how a multivariate Gaussian distribution will change in light of new data. And if you're familiar with the language of Bayesian probability, this is the same as deriving the posterior distribution of a multivariate Gaussian. So the task that we're interested in here can be phrased using this thought experiment, right? Let's imagine that we have a multivariate Gaussian distribution modeling the joint distribution of d random variables here. Now, we get to observe the values of some of them. And what we're interested in is how would those values change the distributions of the other variables? That is, what are the posterior distributions of the remaining variables? And thanks to the nice mathematical properties of a Gaussian distribution, it's amazingly still a multivariate Gaussian distribution. So posterior distribution of Gaussian is another Gaussian with an updated mean and covariance. And we won't be going into the math of what this updated mean and covariance are, but we can take a look at some examples to see how this update procedure actually works. So let's imagine again, right, this bivariate Gaussian distribution here, where the two variables are highly correlated to each other, quantified by this 0.9 covariance value. Again, we can use this parallel coordinates plot to show the individual distributions again. And let's imagine that here we get to observe that the value of x2 is exactly 3, and we're interested in seeing what the posterior distributions of these two random variables are. And here I'll just show the result in orange, right? So in orange here, they are the 95% confidence intervals of the posterior distributions of these random variables. So taking a look at x2, we see that this posterior confidence intervals is very narrow, right? The upper bar and the lower bar is basically concentrated around 3, which actually makes sense, right? Because our knowledge says that x2 is exactly equal to 3, so there shouldn't be any uncertainty regarding what x2 is. So the confidence interval basically shrank to just one single number, 3 over here. But on the left, we also, and this is pretty interesting, I think, we saw that the posterior distribution of x1 changed pretty significantly. So first of all, it shifted up, and then the confidence intervals also shrank a little bit. It shifted up because, right, there's a positive correlation between x1 and x2, and x1 here, sorry, x2 here is taking a positive value, 3. So x1 is also more likely to take on a positive value. So this distribution shifted up. But because there's a correlation between the two random variables, and we are gaining some information about x2, then we should also gain some information about x1. So our uncertainty actually decreased a little bit in terms of what the value of x1 is, which is pretty interesting. And we observe the same behavior where we have a different observation. For example, let's imagine here that instead x2 is revealed to be equal to -2, then the confidence interval of x1 now shifted down to reflect the fact that x1 is now more likely to take on negative values. But the width of the arrow bars, again, also decreased a little bit to reflect our reflect the fact that our knowledge about x1 increases with information about x2. Okay, so in the final case where here there's no correlation between x1 and x2, where this off-diagonal entry is exactly to 0, then what we see is pretty interesting, right? Regardless of what value x2 takes, the posterior distribution of x1 actually matches exactly with the prior, so it doesn't change at all. And this makes sense too, right? Because there's no correlation between x1 and x2, so whatever value x2 takes, that shouldn't affect the value of x1 at all. So the posterior distribution stays the same. Okay, so at this point, you might already see where we're going, where we're trying to relate this back to the original example with the housing price. And the connection here is this, right? We can model the unknown house prices as random variables using a multivariate Gaussian distribution with appropriate covariance values. And then we will use this update procedure to see when the value of one random variable is revealed, how would that affect the distributions of the other random variables? Or how would that affect our knowledge about the other prices, the other house prices? So if we concatenate the price of our own house in Missouri, the price of our neighbor's house in Missouri, and the price of the third person's house in California into a 3-dimensional vector, then we can use this trivariate Gaussian distribution to model the joint distribution of these 3 random variables. And we can use the same parallel coordinates plot to show the individual distributions. And more than that, right? And this is where the fun comes in, I think, where we can follow the conversation that we had in the beginning to see how these individual distributions actually change in light of new data. So if you remember in the beginning, we misheard our friend, right? We thought that our friend meant that the person in California actually sold her house for $250K. Which was pretty surprising, but it doesn't narrow down the range for x1. That is, upon observing the value of x3, the third variable, it doesn't change the distribution of the first variable. This makes sense, right? Because there is no correlation between x1 and x3 as quantified by this value, this off-diagonal value in the covariance matrix. Now, upon realizing that we misheard a friend, right, we realized that the training data or the observation actually meant that x2, the second variable, is exactly equal to 250 instead of x3. So by conditioning or by updating our distributions using this correct information, we are able to obtain this posterior distribution for x1 here, which is a lot more narrow. And that is why we are able to narrow down the range between, which was originally between 100 and 300, and now it's just between 190 and 270, which is a lot smaller. And that's exactly how we were able to achieve that intuitive update procedure using the language of mathematics using this multivariate Gaussian distribution. Okay, so that's the 3D case. But as you can imagine, right, a multivariate Gaussian distribution can model the joint distribution of any number of random variables. So we don't actually have to stop at 3. Let's imagine here that now you are an analyst and studying the prices of 20 houses on a block. And you have this very particular correlation structure that you want to model, which is that nearby houses should have similar prices and far away houses should have uncorrelated prices, which is pretty reasonable. Then you can use a 20-variate Gaussian distribution to model these 20 random variables using, for example, this covariance matrix here, where the entries close to the diagonal have higher values, and the entries far away from the diagonal have lower values. And that exactly reflects the correlation structure that we wanted in the beginning. And what we do, right, is again use this parallel coordinates plot to plot out the individual variables, but also use the update procedure to see how these individual distributions will change in light of new data. So here I'm showing the result when we observe that x10th, the price of the 10th house, is some positive value. And we see this very interesting behavior, right, where the price of the distributions nearby this 10th variable are updated so that the mean takes on a higher value and the standard deviation of the variance decreases. But when we move further away enough, then the posterior distributions are exactly the same as the prior, because there's not enough correlation between the training data and the test data. Okay, so this is where the punchline comes in. We've done the update procedure for 3 random variables. We've done the update procedure for 20 random variables. And now what we want to do when we want to do regression is we want to make our prediction at any input location, any random variable that we like. So by effect, right, in effect, we are extending this multivariate Gaussian distribution to infinitely many random variables, infinitely many unknown quantities. And that's exactly what we get, an infinite variate Gaussian distribution. And that is a Gaussian process, or a GP, where instead of a mean vector and a covariance matrix, we have a mean function and a covariance function. Mean function, you can just basically set it to 0 most of the time. Covariance function, however, some people use this radial basis function, or RBF covariance, that has this very particular form. And what this form does for you is that it will increase when x1 and x2 are close to each other, and it will decrease when x1 and x2 are very different. And that's exactly what you want in terms of the correlation structure. So when we come back to the original regression problem with these 3 training data points, what we can do, right, is we can ask ourselves, what are the test points that we're interested in? Let's imagine in the beginning we're interested in these 3 test points. Then we can use a trivariate Gaussian distribution to model these test points, the labels of these test points, and then use the update procedure to obtain the posterior distributions of these test points based on the training data. But again, we don't have to stop at 3 random variables. Let's say I'm interested in all integers between -5 and 5. Then this is the updated distributions that I'll have. And I can keep increasing the size of this test set to have more increasing granularity when I make the prediction. And in the limit, right, when I have this test set to be a very dense grid with infinitely many test points, then what I'll have in the end is this Gaussian process, or GP. And that's exactly what a GP is. It's basically a multivariate Gaussian distribution extended to infinitely many random variables. Okay, so I see that I'm running out of time, so let me quickly wrap this up. In Python, when you want to implement GPs, you can use this state-of-the-art GP library called gPytorch that allows you to implement GPs in a modular way. So you want to implement your mean function and covariance function. And by swapping out different mean and covariance functions, you can induce very different behaviors that you want. And I'll speed through this slide here because I'm running out of time. And I'd just like to conclude this talk by mentioning this task, which is called Bayesian optimization. And it's an optimization framework for black box expensive to evaluate objective functions using GPs. I actually gave a talk at PyData last year on Bayesian optimization. So be sure to check it out if you're interested in how GPs are used to solve real-world problems. But I also recently wrote a book on this. And in the book, I talk about how the GP can be used to kind of balance between exploitation and exploration to optimize for an unknown function. And there are other topics in the book that I think are pretty interesting. This is a plot from modeling housing prices in California. This is a plot where we combine a neural net with a GP. And since you're at PyData, you can actually use this discount code to get, I think, a 45% discount on this book, on any other Manning books. I'm very out of time, so thanks so much for listening, and I'll be happy to take any questions offline on Discord.